xy, right, equals lambda 2x plus 2y. So partial of, y'all just double check that. That okay? It's 1 o'clock, 2 o'clock. Any ideas? Why am I doing that?
I don't think we can have a zero height or like a zero.
Yeah, it wouldn't even make sense for us to talk about a box if we had any of those be 0. But what am I going to do to my equations? Oh, I forgot to put the fourth equation up there, everyone. Okay, it's up there, all right, here. It's here, there it is. There's equation 4. Okay, so I'm supposing this is true, but it actually has to be true or else we have a volumeless box, right? But it's going to allow me to do what now? Y'all want to divide, huh? Look, there's different ways you can get to this, all right? For some reason, I just keep wanting to go with make this XYZ, make that XYZ, make that XYZ, right? I mean, because they are. So let's see. If we do that, then what does this equation become if I multiply everything by x? It's xyz equals that times x, right? So how about I write this? X lambda 2z plus y. That must equal the same thing I get here when I multiply both sides by y, right? Which would be y lambda 2z plus x. But that must be equal to this when I multiply by z. Z lambda 2x plus 2y. So if I multiply this by x, this by y, this by z, then these three equations must be equivalent. Now what I can do is I can see if there's any way to clean this up. Man, it's looking pretty nasty. Any ideas here?
I mean, maybe you could divide by lambda. I don't know if it would necessarily help.
Yeah, I mean, can lambda be 0? No, lambda can't be 0, right? Do you all agree with that? Because if lambda is 0, this is 0, and that means one of those is 0, but we're saying nothing. Okay, so why don't we just get rid of all the lambdas? Okay? So let's get rid of the lambdas. And if I get rid of the lambdas, I'm going to have this. 2xz plus xy equals 2yz plus 2xy. What did I do there? Yeah, I got rid of the lambdas here, right? And then I distributed the x through, and I distributed the y through. And then,
Oh, is that supposed to be 2xy, or should that just be xy?
where is that?
Right. No, other to the right.
Oh, this one right here is just xy. Thank you. Let me just continue with it. I'm going to do the last one here. 2xz plus 2yz. So I would have that this must equal this, must equal this. Anything?
Just there's x, I see xy. I see.
Yeah, like if I just look at those two, right? Then the x times y's cancel from both sides.
Yeah.
Let's work with those two only first. So if we work with just those two, we get 2xz equals 2yz. Take everything to one side, and let's get rid of the 2, right? xz minus yz equals 0. Factor out a z. Z times x minus y equals 0. And that means that either z is 0, oh, can't be, right? Or x equals y. So you see I'm not even considering z being 0 because I already said z can't be 0. So if I work with just those two, I know that x has to be y. And what if I work with these two right here? What if I work with, will these two cancel out? Yeah, these two will, won't they? So if I work with those two, I would get, what cancels? These? And you would get xy equals 2xz. And then move everything to one side, xy minus 2xz equals 0. Factor out an x. Y minus 2z equals 0. And we can't put x equal to 0, so y must equal 2z. All right, so as long as none of our variables are 0, which is the only thing that makes sense in this problem, then we work through, we do all this, and we get these two nice relationships have to be true. Now what? Now what? We still haven't satisfied the fourth equation, right? So why don't I go in and why don't I replace y with, no, let's do it this way. Replace x with, no.
Yeah, x and y.
Replace x with y, and then over here, we're going to replace z with 1/2 y. Okay? And then we'll have one equation with just y in it. Right? So equation 4 now tells us that we have 2 times x, but what's x? Y. Times z, but what's z? Half of y. And then plus 2y times z, but z is half of y. Plus x, but x is y, times y must equal 12. That's wild, is that what you said? Yeah. Okay, so what do we get? Y squared plus y squared plus y squared equals 12. So 3y squared equals 12. So y squared equals 4. So y equals plus or minus 2. But we're not going to have a negative y, right? Because it's the length of a side of a box. So y is equal to 2 is the only answer that makes sense. And if y is 2, what's x? X is 2. And if y is 2, what's z? 1. How do I know that that's the maximum and not a minimum?
Do we have to plug it in?
Yeah, we're going to, it doesn't ask for the, oh no, it does ask for the volume and it asks for the dimensions. We just found the dimensions. But how do I know that that's the maximum volume?
Because the minimum is 0.
The minimum would be 0, okay? The minimum would be 0. But it's not asking for that. So let me see here. My box that I drew. Hold on. Okay, so basically it looks like this. Your x is 2. Your y is 2. 1 like that. So this is 2, and that's 1, right? That's what we found? So what's the maximum volume? 4. So the maximum volume is the volume when you have 2, 2, 1, which would be 4. 4 cubic meters, right? 4 cubic meters, because it's a volume. And confirming surface area. Let's just confirm the surface area of this. Let's just verify it. What's surface area of that? 2. This one? 2, 2, 2, right? So 2, 4, 6, 8, and then the bottom
4
is going to be another 4, so you get 12, and there's no top to it.
square.
So it's a square base, but not, the height's not the same. Now, if this had a lid on top, if it did, then all 3 of our dimensions would have been the same. So the way you get the maximum volume would have been to make it all sides equal length. But because it didn't have a top, we had to account for that somehow, so one of the sides was shorter. Make sense? All right. Yeah. Let's not go through this whole problem. Let's just take a look at the setup for this one. Find the maximum volume of a rectangular box with a double bottom if it is to be made from 81 square feet of cardboard. What are its dimensions? So this is basically the same thing, but what's different in this problem?
Double bottom,
Double bottom, right?
and you have a top too.
And it has a top, so this doesn't say that it doesn't have a top, right? So we still have a box like this. We don't know its dimensions. We can still call this X, Y, and Z because the volume is still just length times width times height. What changes is the constraints different now, right? What's the area of this one? Well, we have that right there, which is XZ, and we have 2 of them. Plus, and then we have this right here, which is YZ, and there's 2 of them. And then we have the top, right, and the bottom, but we're doubling up the bottom for reinforcement. So 2 layers of cardboard there. So we have, that's what, X, Y, 3 of them. So that's your new constraint. So now your grade, equals what? This is going to have to be equal to 81. So you just have a different constraint, so your gradient, your partials of G are going to be different a little bit. Not much, just the constants are going to be a little bit different, which is going to change your constants when you go and solve. But all this setup is pretty much identical. Make sense? We won't work through that. Here's one that's more applicable to the real world, physics type thing. You have a sphere, and you have a point. So here's a sphere, and that point is not on the sphere. Can we verify that? Plug this in. 9 plus 1 plus 1, that's not 4, right? So that point does not live on that sphere. Got a sphere, got a point. Find the point on that sphere that is closest to that point.
And farthest.
And farthest. Ooh, yeah, 2 of them. Yeah. What's that?
I was just talking to myself. I see where you're doing it without going through the whole range thing, but I understand that's like something.
How would you do it without doing the Lagrange?
Since it's the sphere with radius 2, what I do is I find the vector from the origin to that point, and then multiply that vector. I would basically find the constant that I need to multiply that vector by to get that vector's magnitude equal to 2.
Yeah.
So that's pointing, so that second vector I have, that's guaranteed to point to something on the sphere. And since it's in the direction of that point, logically, that vector is pointing to the point closest to that point, and then just.
So it's basically some scalar multiple of that.
Yes.
You basically need, yeah, that would work, I think. All you'd need is to scale this. I like this idea. We're not going to do it this way. Because if that sphere is not centered at the origin, this doesn't work as easy.
Yeah, it's a little hard.
Yeah, it's a lot harder if you're not centered at the origin because you can't use the radius to your advantage anymore. So what you're saying is, let's see if we can do this and draw a picture real quick. Here's the center, here's our point, right? You're saying draw this vector. Okay, we'll call that vector V. What is that vector? 3, 1, -1, right? And then what we're trying to do is find some scalar multiple, right? Like this.
Yes.
Okay, we're trying to find that vector. So let's call that vector W. What we need is that the length of W has to be what? 2, the radius of the, right? Now W, by definition, W is some scalar multiple of V,
Yes.
right? W is some scalar multiple of V. So W is 3C, C, -C, isn't it? I don't know what C is, but it's got to be a scalar multiple of that. Now you take the magnitude of that. What's the magnitude of that? Square root of 9C squared plus C squared plus C squared. 11C squared must equal 2. So square both sides. 11C squared equals 4. So C squared equals 4/11, which means C is equal to plus or minus 2 over root 11. You could rationalize, but who cares? Now just take that in there. Boom, boom, boom. Yeah, that would probably do it. So we don't need to do this Lagrange, I guess, right? If it was centered at the origin, this would work out that way. If it's not, that wouldn't work. So let's at least set it up, okay? So we can see the setup of it. This is, what do you have, what are we trying to find the maximum or minimum of? The distance. The distance. So I need a formula for the distance. So what is the distance between, what is the distance between any 2 points? If I have a point here and I call it x, y, z, and then I have the point that I'm looking at, 3, 1, -1, what is the measurement of that distance right there, d? We'll call it little d. It's just your distance formula. Square root of the difference of the x coordinates squared. So how about I do x minus 3 squared plus the difference of the y coordinates squared, and then plus the difference of the z, so z plus 1 squared. Right, that would be our distance function. Do you agree with me that the distance is a function of x, y, and z? And that's what we are trying to find the maximum or minimum of, right? What is the constraint? That you have to live on the sphere. See, this point is arbitrary, isn't it? But if I constrain it and tell you that that point has to live on this sphere somewhere, then I add that constraint. Right? And this becomes my g of x, y, z. So gradient not looking fun, right? Gradient's not looking fun there. Imagine taking the partial. So this is something that you may see later on in a physics class or somewhere else. This comes up often enough that we need to understand something. If you're ever trying to find the max or min of the distance function, then you can actually look at the distance squared function. So like whatever x, y, and z make this the biggest means that it's the x, y, and z that makes the radicand the biggest, right? The square root doesn't really matter because the biggest this value is, the square root of it's still going to be the biggest you would get. And then the smallest this is, the square root of that's still the smallest. So in other words, what we like to do is we start a new function, d, which is actually d squared. And we try and find the maximum and minimum of capital D, which would be this without the root, which is easier to take your partials of. Does that make sense? I'm not going to do that, but unless y'all want to. Nah. Yeah, we won't do that. Oh, by the way, back to that, we got that 1, right? We did that with the vector. I think we got that point, right? How would you get the point furthest away? It's pointed the opposite direction, isn't it?
Yeah.
It's on the opposite side. So it's just that vector multiply by -1. Should flip it over, point it in the opposite direction. You know what? I'm going to see if my computer can do this real quick. I have an algorithm in here. Where are my calculators? So that was, was that it right there? Yeah, that's it right there. Hold on. Do you remember what the answer was that we got? What was C? Was it 2? It was 2 over root 11, right? And then the point was the point 3, 1, -1, right? So if you multiply this through here, you get 6 over root 11, 2 over root 11, and then -2 over root 11. So you can see the computer found those same solutions. Yeah, so the work is a lot more challenging to do with the Lagrange. All right, one last thing, and we will be done with Lagrange. At least we'll be done talking about it. You won't be done until you do your homework. All right, so what if we have a function of 3 variables, again, but instead of having a single constraint, we have 2 constraints. So remember we had the problem that started off the class, and I tried to give you the idea of like you have this eggshell and you have a temperature, right? Well, what if instead of having an eggshell, right, this is a 3-dimensional eggshell, what if I have another surface like a plane? What if I had a plane that cut through that eggshell? This equation of the plane has 3 variables in it, doesn't it? And it would, we know plane equations, what they look like. And this right here is a quadratic surface, right? So individually, these two are like these 2 constraints. Do you all see that? The plane and then the egg. Where the plane and the egg hit each other is where the plane cuts through, the egg, creates a path, doesn't it, a curve? And so what we're doing is we're saying, hey, look, find the maximum temperature, not on the surface of the whole egg, but on the egg, but also on the plane, so on their intersection. Do you all see that? So now you can only live on these points. You can't live everywhere on the shell. Yes?
So how many constraints can we actually add to this? Like,
Well-
can we do another plane slicing through there, and then another surface or something?
You could, so that's a great question. If we try something else, we need to have an intersection. Like we need to have something they have in common. So you could theoretically have more so long as the shape you have, where they hit each other, is something more than a single point. Because if they hit, like let's say you take 3 planes, like let's say the XY plane, or all 3 planes where they hit would be like the origin. And if you're trying to find the maximum of a function at a single point, well, it only has one value. It's both the maximum and the minimum. So you can have more as long as where they hit each other is something worth looking at. Does that make sense?
Yeah.
Okay. All right, now, so what do we do when we have 2 constraints? Well, here's the big here's the big difference. Instead of doing gradient of f equal lambda gradient of g, because we have a second constraint, we have to have that this gradient is not only equal to some scalar multiple of this gradient, has to be that plus some other scalar multiple, mu, of the gradient of the second constraint. And then we have the two constraints must be satisfied. And so all in all, we're going to have lots of equations. We're going to have five equations. So just to be clear, when we say the gradient of f has to be equal to this, it means partial of f with respect to x has to be lambda partial of g with respect to x plus mu partial of h with respect to x, and then we do that for each partial. And then we have our two constraints. We do an example, all right? You'll kind of see it. We don't do an example. I thought I had an example here. I don't. Anyone have the book? Can I borrow that? Let me see what there is here. I don't know why there's not an example there. 11.8. Okay, we'll do that one. Let's say we have the function f of x, y, z equals x squared plus y squared plus z squared. And we're constrained to x minus y equals 1 and y squared minus z squared equals 1. All right, thank you. So let's just try and wrap our heads around what we got here. This is some function of three variables. Again, I like temperature. Temperature is something that kind of makes sense. We have a temperature at every point. Then we have two constraints. We can't just be anywhere. We have to be where? What is this? It's got to be in three-dimensional space. So this is a plane, right? Even though the z's not there, right? It's flat. Your z is always 0, right? Or sorry, your z is free is what I should be saying. So it's like a line, but then extends in your z direction, both directions forever. Here, like this. Let's say this is x and this is y. Then this is the line. This is actually in two-dimensional space. This is the line y equals x minus 1. Right, that's what that is. So that would be your x, your y intercept is -1, has a slope of 1. So it's like a line like this. Hope you all can see that. That's laying flat on the ground. Do you all see that? Yeah, like just in the xy plane, looks like that, roughly. Okay, but your z is free, because there is no z in this equation, right? Your z is free, which means this is a plane that's cutting through, whoosh, like that. Okay, so your point you're looking for the max or min temperature on this plane, but not only in that plane, you also have to be where? What is that? In two-dimensional space, it's a circle, but in three-dimensional space, it's yeah, you have a minus in here, so yeah, it's like kind of like this, but remember, I can't draw it. It's gonna be hard to draw. But it's where this surface hits that plane. So you only have certain points. I'm not gonna be able to draw it, all right, unless I use the computer. Are you all right with that?
But it will hit it, so probably we'll have two lines.
It'll look like probably two like ellipses or something like that. They won't be straight lines. Let's see, 33. Yeah, let's see. Let's try and do the math first. And once we do the math, maybe if we have time, I don't think we will. But let's see, maybe this will work out real nice. All right, so let's call one of these G and one of these H. So I'm going to call this side here G. That's G of x, y, z. And right here, this is H of x, y, z. All right, so first thing I need, first equation, is I need the partial of f with respect to x to be equal to lambda, partial g with respect to x plus mu, partial of h with respect to x. Let's get that. So what's that? 2x equals lambda. We're doing g with respect to x. So 1, and then plus mu times h with respect to x, and there is no x there, so 0. So we're not going to have anything there. So basically, this is just 2x equals lambda. Isn't that nice? Okay, equation 2. Partial of f with respect to y equals lambda partial g with respect to y plus mu partial of h with respect to y. So 2y equals lambda times, what's partial of g with respect to y? -1. So how about just negative lambda? And then what is the partial of h with respect to y? 2y, so plus mu times 2y. That makes sense? What I'm doing there? Okay, third equation. Partial of f with respect to z equals lambda partial g with respect to z plus mu partial h with respect to z. So 2z equals, what is partial of g with respect to z? 0, right? So I'll put lambda times 0 just so. And then mu, what's the partial of h with respect to z? -2z. And then what are my fourth and fifth equations? These, right? So this is equation 4, this is equation 5. All right. Let's clean up the ones that are easier here. 2z equals -2 mu z. I like that one. I like that last equation. Look at that last equation right here. If I move everything to one side, let's get rid of the 2's. Move everything to one side. Z plus mu z equals 0, right? And then factor out a z. Or, yeah, we can have z equals 0, or mu could be -1. Man, let's go with z being 0. Yeah, so if z is 0, we can go get y. And once we have y, we can go get x. So suppose that z is 0. Then equation 5 tells us what? That y is equal to plus or minus 1, right? So what if y is 1? What does that tell you x is? Equation 4 tells us x is, if y is 1, move it over, x is 2. Right? So we have 2, 1, 0, and then there's some lambda and some mu, right? And I don't really care what those are. But that wasn't the only thing. I could have had
-1 for y.
-1 for y. If y is -1, then equation 4 would have told us what? X is 0? Yeah. So we have another one, which is 0, y is -1, z was 0, lambda, and mu. Now Now let's just make sure that we don't have any problems here. This is all coming from the third equation. I don't think I have any problems with these two. If x is 0, that's okay, because then lambda or mu could be 0. If y is 1 or -1, then yeah, okay, so we should be able to, looks okay. Now, we've only looked at if z was 0. What if mu is -1? What if mu is -1? We haven't looked at that yet. I have 2 minutes. If mu is -1, then what can you tell me? This equation 2 becomes 2y equals negative lambda, and mu was, yeah, so minus 2y. So that would tell you that 4y equals negative lambda. If I move everything to one side.
Yes.
So lambda is negative 4y. And what can I do with that? Oh, wait, woo, what? Sorry. Negative 4y equals lambda. What can I do with that? What about equation 1? What would equation 1 become? So equation 1 would become, this one right here would become 2x equals negative 4y, which means what? Do y'all follow me what I'm doing here? Yeah. If lambda is this, and put lambda in right here, then you get that, but then that would tell you that x is equal, that would tell you that x is equal to negative 2y. And then what can you do with that? Equation
Equation 4.
Equation 4 would tell you, what's that? Did we know that x was 2?
Right there, the second area on your right there. Equation 4x equals 2.
Where, here? No, no.
That's
This was all under the assumption that z was 0. So I was looking, remember we had to look at these two. So z was 0, we were in business. Then I was going back and saying, what if mu is -1? So if mu is -1, and I go here, I'm out of time. Do you see how you get it from here though?
yeah.
Like once you go to equation 4, you have y here. Once you get y, you can plug y in here. Then you get z. You've got x, y, z. You compare them all. All right, well, that's it for Lagrange. The homework is messy, as you might imagine. Do your best. We move on to the next chapter, next class. Does anyone need their test? Did they all get around to everyone? All right. Everyone have a good day.
So actually, I don't even have the